Okay, so recording has started. And what we shall do today is, of course, as I said, anisotropic media. We just started the discussion yesterday. Today we're going to take it forward. We are just basically going to show what it is, the basics of anisotropic media and, some of the properties of the well-known dielectric tensor that is basically the main difference between dielectric, between anisotropic media and isotropic media, namely that the dielectric constant does not remain like a constant, but it has actually dependence on direction, which I think you guys are aware. Uh, oh, what did I do? One minute. Oh, I did the wrong thing. Sorry. Yeah. Okay. So can you see the screen?
Yes, sir.
Okay. Okay. So we had a little discussion about what is anisotropy and all that. In the sense, anisotropy, what is the meaning of isotropy and all that, and we kind of came to the conclusion that I'm sure you guys have done this before. Homogeneity implies isotropy and not vice versa. So now we go directly to the main content of this anisotropic media in terms of optics. So again, the whole premise is that there is light which is incident on a medium, and that generates polarization. And I mean, of course, the medium has a susceptibility, but the basic thing that is, that is the difference between isotropic and anisotropic media is that the susceptibility depends on the direction of the input field, and that is what we're going to see today. Okay, so we can just start off by realizing that your polarizability, which we write as was this in general for, I think I should write for isotropic media, or okay, no, I think we can write this as a general statement. This is fine. Inside, of course, we have other stuff. So this is the green function that we studied in the Kramer's chronic stuff. And here, of course, and we also know that, assuming your time invariance and causality, we can, of course, write that t and t dash, is the t dash has to be before t, right? So basically, this is the correct statement where we now sort of, so this is basically where we start from, okay? E j t dashed, dt dashed, and again, some the Fourier domain and all, how these are related. Of course, in Fourier domain, you have your P of R omega as some epsilon R. This is the crucial part, okay? This is the crucial part. This is the crucial part. So basically, sorry, not this. This Fourier transform. So you know that this is related by this of Ej and Ej of omega and Ej of t are related by Fourier transforms. That is absolutely fine. But the important thing that we have for your anisotropic media is basically that this is not a constant anymore. Different directions of, so I, J essentially correspond to different directions, and this will vary. So, depending on whether this is X, Y, Z, whatever, This is not going to be the same. So this is now like a tensor. So we shall just again quickly write down another sort of, again, in general, we have importantly that dj of r omega is this, the displacement. So we shall actually find out that when we talk about this is the one that is actually that this assumes much more importance compared to this. Okay, and we basically just the relation that you will find in most books would just be that this is something like epsilon ij ej r omega. So where this is now a matrix, this is not a constant anymore, this is a matrix. So we can probably just write down at
Elaborate
this
on
point
the
of time
IJ part.
a few any questions?
Hello.
Yeah.
Sir, can you elaborate on the IJ notation? What is that?
Yeah, I will come. It's space. So X, Y, Y, Z. Just bear with me, Hitesh. I'm going to come to this very quickly. So we're going to write what this is. IJ essentially are spatial coordinates. IJ, let me, I can write down.
I have a problem with this free index and the dummy
Uh,
index. Like on the right hand side, you have 2J and 1I, and on the left hand side, you just have a J.
yeah. So well, this
Summation of
notation
J.
clarify when we go down. Okay, very quickly. I mean, just essentially we are summing over this. So essentially, it's going to be matrix. So this is going to okay. In this typically what we have is epsilon ij is 3 by 3 ej essentially corresponding to different polarizations, it is different coordinates, and this is a tensor which is essentially a 3 by 3 for more, or I mean for any material, this is a 3 by 3 matrix, and this is essentially a column vector. Okay, so we xy when we just I'm going to just bear with me a little bit. Okay, what I'm trying to say. So
Sir,
I
I
think
think,
we'll just
sir, I think Hitesh is suggesting it to be DI, as far as I can understand.
oh, okay, yeah, that is correct. Acha, ha, that I agree. Acha, that I agree. Yes, that I completely agree. That is absolutely right. That is absolutely right. Let me rub the whole that right. Very, yeah, that is very right. Absolutely. Notationally, this is not correct. Okay, so some of these things I'm preempting study this in, but basically, anisotropic medium, uh, what does it? Okay, C is not in the direction of E. That is quite plain because you can see that this is when this is a matrix. One, one particular D will actually it will actually have represented J's. So big, so obvious consequence would be D is not in the direction of E. Also, very crucial, the direction that is extremely important. Polarization direction is something which is different from stuff.
Sir, your voice is breaking.
Oh God! So I am in the I am at IZER. So is everybody finding the same? Are you finding my voice breaking?
Yes, sir.
Oh God! I'm having
Sir, now
yeah.
it's
I'm
okay, I think.
land, so I mean, I absolutely cannot help. I mean,
Frequently.
I can probably go out and come in. What? Yeah, I absolutely helpless. Can't do anything. What is it? Kind of stable now?
Yeah, it's stable now.
Yes, sir, now it's better.
Okay, okay. So polarization direction is not the direct of E. again, extremely interesting, very, very interesting. We typically, what is the thing that we have, polarization? It is the tip of the electric field E, right? Whatever that, what a surface that inscribes, that we define to be the polarization vector, right? So that is actually not the case here. Instead, what you have, polarization directions, okay? And that is very interesting. There are two polarization directions which exist for the same wave. Directions, we are going to unravel all this, but I think it is important for you to just sort of first, know what the hell this anisotropic media, it is so crucial. It is so completely different from isotropy. So it is like, again, I'm telling you the last page of the book, and we are going to reach all these step by step so that your curiosity is awakened. And I will actually today, I will upload the references that I have used for this. And if you want, you can read that so that we can have better discussions. Okay. Exist, and very importantly, the refractive index also is different. The refractive indices are different in those two directions. Okay. And the wave has two different velocities in the two directions. Very important. And then there is the concept of a refractive, an index ellipsoid, which is something that is basically a surface where the wave energy is a constant. So that is something which we will, this is where we shall hopefully end today's class, where this is like a surface where the total energy density is constant. And this is extremely important because when we, the different types of crystals that we will deal with, and the crystals, when we deal with different types of crystals, essentially they have different types of symmetry. Okay. And that, so we call them uniaxial and biaxial crystals. So what they mean is basically connected to these 2 points, this point and that point. So biaxial has less symmetry than uniaxial. So they have like two different, 3 different directions where the velocities are different. Uniaxial is less complicated than that. So it just has you might have already at least encountered before. The sort of those crystals which give you an extraordinary ray, an ordinary ray, and all that. So these are things that you know, but I don't think you've studied the theory, the physics in too much of detail. But the degree of symmetry here is higher than this. So uniaxial and biaxial essentially correspond to these number of polarization directions. And so when I say generally, it's those uniaxial are more common. Okay, most of our polarization optics that we have, half-wave plates and all that, they are mostly built on uniaxial crystals, built around uniaxial crystals. Okay, so this is again, this is basically what we should have learned by the end of. This is what we shall learn by the end of our discussions. Okay. So, and as you see, these are
I am kind of lost where what we are doing because uh, it didn't connect the way we define
so
the.
basically, right. So what I'm saying is that this is essentially what you have. Okay, this is one relationship. The consequences of this are all these. Okay, this is what is going to lead to all this stuff. This may be
Okay,
looking as a very simple equation, but because of this thing not being now a number, essentially you'll have all these very, very pretty exotic kind of statements and pretty exotic phenomena. All the root of that is this simple equation that we have. Okay, this is
Okay.
extremely powerful.
Sir, what is I
Okay,
and I and J?
yeah. So I and J are spatial coordinates. So basically X, Y, Z.
Then what is
Okay,
R?
are spatial coordinates. Sorry, R.
And then R.
No, this is R is of course your root of that thing, right? This is essentially your so basically when we say the Fourier transform, so R T dash and is essentially R this thing. So yeah, so we will come to that. I mean, we'll just define everything properly in the sense that we have so EX is the input field, okay, and R
Okay.
that we define is in the coordinates of the crystal.
Okay.
Okay, so that is very crucial. So that is, yeah, that I think, yeah, I should have mentioned before. So basically what we're going to see is that the susceptibility, which is essentially something which induces your polarizability, that depends now on the input field. So there are two different things. One is what polarization or what dielectric constant the input field uh, uh, basically experiences inside the crystal, and that is in this, whereas R here is the coordinates of the crystal itself. Okay, so these directions are kind of with respect to the field, right? So this will get clearer as we go ahead, especially when we shall define, when we go to this energy density part and all that. Why is this so small always? It does not show. Anyway, let's start. Okay, so basically what I am writing, what I was writing is something like this: vector D is this epsilon naught, epsilon R tensor E, where this epsilon R essentially is nothing but this. XZ, YX, YY, YZ, and ZX, ZY, ZZ. Okay, so essentially what we have is dx is epsilon naught summation over I, if I say xi ei, I is xyz. dy is epsilon naught epsilon yi ei, and dz is epsilon epsilon zi ei. This is the crucial part. Okay, so the moment you have something like this, you will always have, if you have this kind of a coordinate system where these are 3x3 matrices and you have everything all different and all that. So there is always a possibility to diagonalize this. Okay, you basically have, there is a procedure there can be a procedure of completely, getting rid of these off diagonal terms. And of course, for doing that, there needs to be some properties that these need to obey, but a very sort of a common thing that is done in the case of crystals as well is the process of diagonalization, where I tend to just have these terms, and so I do something where I completely get rid of the off axis terms. And when I do that, I get to this kind of a matrix where I only have these three diagonal terms, and that is typically known as the principal axis of the crystal or whatever, or of the material that we are dealing with. Okay, so this is something again that we will do look at, but what if I, principal axis, for example, is, I mean, you might have, this is also known as the optic axis or the principal axis. Yeah. So you might have studied it with respect to, knowing that this is something along which the refractive index is not modified, all that side of thing. But when I go to the what it actually means in terms of mathematical or mathematical treatment is where I do a diagonalization of epsilon r is essentially going to a principal axis coordinate of the material. So when this is again something that we are going to look at. So basically you have, in that case, just this epsilon xx, epsilon yy, epsilon zz, and you have nothing here. And then you have your d given by these ex, ey,
Sir, I have a question.
ez. Yeah, sorry?
I have a question.
Yeah.
Yeah, so here this epsilon xx will not be the same epsilon xx
No,
as
no,
it
no,
was
no,
in
no.
the
This is
refractive index.
modified. Of course, of
Sure.
course. This is modified. Yes, this is obviously modified. Of course, this is, so I don't know. Maybe we write this as some capital something. Okay, this is obviously different. So let me write, this is, so let me just write this equation number, maybe 1 epsilons are different from those in 1. Okay, so this case you have typically what we will sort of specify here is that these, so these epsilon capital X, capital Y, capital Z, these are the principal dielectric constants, and the same, absolutely same treatment you have for the susceptibility as well. For your, say, for chi, and you have something called chi x, which is like the principal susceptibility constant or whatever, principal susceptibility of the material. Okay, and of course, yeah.
And the ex, ey, ez also that you've written is the transformed this thing, right? Not the same ex, ey, ez that we used earlier.
See, when we do the when we are doing the
diagonalization, we are basically going into the basis of the eigenvectors, right?
Correct. So, okay.
Ey, ez also will be different on the basis of eigen, basically the transformed.
So basically, see, what we do, that may not be the, see, what we do, Anirudh, typically when we have this matrix here, see, you are writing everything in terms of the principal axis coordinates. Okay, so in the sense that you have this matrix existing, this is not dependent on the electric field. Okay,
Yeah,
so this is independent. So I can always diagonalize this independently of the electric field, right? So once I go to the principal axis coordinate, you can say that whatever electric field I come in from outside will lead to a displacement field that is different from what happens when I have this. Okay, so basically I'm trying to say that this is the dielectric displacement field, which is essentially the field inside the crystal, which is brought about by the electric field that is incident. When I go to the principal axis coordinate system, the dielectric field that will occur in the system is not going to be the same for the same electric field that is incident. That is a better way of saying, because this is an input, so this will always be independent of what material it is. But the field that is induced, that I am choosing, if I go to the principal frame, then whatever dielectric field that is induced inside will absolutely be in terms of that, of this principal axis field. I mean, axis coordinates. That is a better way to say. Okay, so you can say that when we are talking about these eigenvectors, Anirudh, it is probably better to think of things like, as we said, that A vector, that time, that material vector or something. So that is
Sir, my
basically.
only point was that the electric field that we have written here will be in the basis of the eigenbasis, and the earlier one would be in the normal basis that we had selected.
Yeah, so I would say that
So
this is the one
Ex,
that is.
Ez would be more like Ex prime, Ey prime, and Ez prime in some sense.
But then if that is like an input, I mean, see, this is not an eigenvector of this at all, right? So this is an input, right?
I'm not saying that is the whatever you've written is an eigenvector.
Okay, yeah. In the sense that if this is
The
changing, then
coefficients
these
Ex, Ey,
also
Z
should
will
change.
be coefficients in terms of the eigenbasis.
Yeah, okay. Coefficient wise, but then see that treatment is so different from here. Yeah, we are not talking about expected probabilities and all that here at all, right? I mean,
Not
when
probability.
you're yeah, so when we are measuring in the principal axis coordinate system, we typically have a displacement field that is different from when you talk about a normal, I mean, undiagonalized or I mean random. But then see, this is the one that is always typically encountered. I mean, this is what. But then of course depends on the symmetry and all that. We're going to go into that. But essentially, I think bottom line is that I can diagonalize this independent of the electric field, but the dielectric field also will be different when I have the same electric field that is incident on the material if I go to the principal axis frame and if I don't go to that. Now, if I strictly, if you talk about a mathematical equation, then obviously, yeah, if I just chose this, and the same thing I write here, then from what you're saying that, yeah, but that is only if I think of this as an eigenvalue equation, right? This is not that. Absolutely not that. This is not an eigenvalue equation. This is basically the dielectric field that is caused when I have an electric field that is incident on the material.
Mm,
Okay, so that is, I think,
Sir,
what is crucial.
I think he's saying that electric field vector, physically that vector is the same, but the
Yeah.
coefficients, because you have changed the
Hmm.
basis, the coefficients are different.
Right. The projections are different. That I agree. Absolutely right. The
So then,
projections will now be different. But that
it
is
won't be.
manifested in the D, na?
So I'm saying even all the coefficients of T are different, even the
Yes.
matrix is
Yes.
different, and
Yes.
even the
Yes.
electric field is different. But the equation is still D is equal to epsilon into E.
Yeah. If I directly have this and okay. Yeah.
So,
If I
like
say that.
for example, if you
Uh,
have a crystal that let's say
hmm,
which is already diagonalized along X, Y, Z, okay.
correct. Correct.
Now let's say you're looking at the front face, and
Hmm.
instead of considering a vertical and a horizontal axis, you take a 45
Okay,
degree
okay.
rotation.
No, I agree what you're saying. Yes, yes. Then the component of the electric field in that
So
will actually be
and
different.
let's say
Yes, I
you
agree.
you had vertically polarized light,
Uh,
so you would write
right.
electric
Right.
field
The
as just
angle, right. In the sense that
100
yes. So
kind of.
basically, you're saying that if I have a crystal like that, and if I have this normal and come in with electric field like this, and now if I have the crystal like this, and then if I have the same, so the normal now is like that.
No, I'm keeping
Then
crystal constant. I'm just changing my
yeah,
axis
that's
length.
what I'm saying. So okay, yeah, let me not draw it like this. Yeah, I should not draw it like this. So it should basically
And instead
be
of a light ray, just draw
yeah.
polarization
Yeah,
entering
so
each of the
basically you can say
stations.
that I'm having one like that and the other like this. So this was my axis once and now this is my axis. So
Yeah.
then this will be like that. Yeah, that is actually correct. Yes. So basically the component of the field in this will be
Ah,
different. That is
so
completely right.
whatever,
Yes.
so the
Right.
components of electric field will change. So instead of Ex, Ey, Ez, you'll write
Yes. I agree. That
X
is
prime,
probably
Ey prime,
correct.
Ez prime.
I agree. Yes. Basically, what you're saying is that, yes. So with respect to that axis, the component that it sees is different. Agreed. Did the class appreciate? This is a very nice discussion. So essentially, if I take this, I was measuring the electric field in the frame of the crystal, in this axis, and then I had some electric field like this. Was first my axis O. Now I rotate this by some I tend to some phi rotation. I just I make a rotation to O phi. Then this is my O phi. O phi, then this is now actually the coordinates of E in this axis will essentially become
The electric
sort of
field will
E
be the
dash.
same, but the components
Yes.
on the
Components
basis
will
will be
become E
different.
dash, right? Right. So basically, so components of E initially, so this is my first picture and this is my second picture, initially in 1, where along O, I should say, along O, where Ex, Ey, Ez, but that in 2 along O dash are Ex dash, Ey dash, Ez dash. That is very correct. That is true. Yes. Right? Huh. Bolo.
So experimentally, what does going to principal axis coordinates mean?
So experimentally in, see that, okay, so basically what that will mean is that you are going to the minimal description of the system where the polarization etc will all be, so essentially you're throwing off the off diagonal terms, right? So you are having some kind of a, just so it's like, throwing out the interaction elements. So if I want to make it simpler, I am going to the simplest possible direction, I mean description of the system, where so if I think of so yeah, okay, so you can say that when I think of a quarter wave plate, so when I actually want to, we typically say that in order to get the quarter wave plate to work properly, you have to align with respect to the we know that it is 45 degrees, the angle, the rotation that you have is 45 degrees of the electric field, right? I mean, basically the optic axis, you have to initially align the beam with respect to the optic axis, right? It is only then that the phase between Ex and Ey will be 90 degrees, right? So this is basically something like that. So you are essentially rotating, you are ensuring that the electric field is along the optic axis, so that exactly what you get is the same, the refractive, there is going to be a phase difference between Ex and Ey in such a manner that the resultant electric field is going to be circularly polarized, right? So it is basically something like that, that this is, you are rotating so you have, your angle of incidence is 45 degrees now with respect to the quarter wave plate optic axis. So that means that you just now have a fast and slow where exactly the phase difference between the Ey and the Ex are going to be 90 degrees, right? So then you get perfectly circularly polarized, right? If you put it and of course if you are at 0 degree, then you get no change, of course. But when you are trying to have that quarter wave plate as a birefringent material, you have to basically, you are ensuring the, you are manifesting the birefringence or the uniaxial property, right? So that basically when you are going at 45 degrees is manifested exactly like this. Okay. So one important thing that what we will look at now is that, so maybe I'll go to a new thing because it's a new topic. So what is very crucial is the fact that Qij, your chi ij or susceptibility will depend on the direction of E. Very crucial. In general. But if there exists cubic symmetry, it will not. And that is what we're going to see now. So basically, in that case, you will the displacement of vector, if we say, that is going to be parallel with respect to the displacement something whatever in response that is going to be parallel to the incident, which essentially fact that the chi of electric field. So how? So let us just start from absolutely basics. How is that happening? So for that, you just consider that, see, when you apply an electric field to the crystal, it will displace both the electrons and the nuclei, right, from their equilibrium position, which is in the lattice. And there is this kind of net dipole moment per unit volume, like that, right? So that is how you basically get, that is the response, yeah, but that is how the material behaves, right? Because there is this polarizability. So basically, when E is applied,
Sir, your voice is breaking a lot.
there was a power cut here. I just told you. So whenever there is a power cut on campus, temporarily we are getting internet to work. Is it fine now? There was a power cut yesterday.
Sir,
Is
I
it
couldn't
fine
get
now?
what you said in the last 15
Okay, so
seconds.
what I said, oh yeah. So whenever we have a power cut, oh man, it is horrible. So what I said basically was that when you, this is standard, nothing new. So when you apply E to a crystal, when you apply it to a crystal, displacement by electrons and you can say ions from their equilibrium positions in the lattice and causes net dipole moment. That is what we know. This is what we call the polarizability as well, right? Dipole moment per unit volume, and this is called the polarization, right? So now if I may write this, basically means my P some summation over J, some Nj Ej delta Rj. Now here when I write this, I'm actually making an assumption that when I am using optical frequencies, typically the ions are so heavy that they are displaced very little. Okay, so typically it is only the electrons which contribute to the response. Okay, so this Nj, of course, is nothing but density of species with charge J, and this is the most general equation. Okay, and now very crucial is Rj. So what is Rj? Rj is the displacement. This is what I was saying. This is the crucial, that R that I wrote. Displacement of this charged species from the equilibrium position. Charged species from the,
Sir, those charged species are essentially electrons, right?
yeah. That is, I'm going to state that from the, yeah, of course. Okay. So that is what I'm going to write now. So basically at optical frequencies, only electrons will contribute, because obviously your ions are too heavy. Electrons will contribute since your ions are just too heavy. Since ions are too heavy, the inertia is too high to follow the field oscillations. Okay. So now please listen to this argument. Okay. So basically I'm going to say that if I have at equilibrium, the total force that the field applies has to be balanced by the restoring force on of the electrons, in the sense that we know that this is a mass spring model, right? That is, of course, that is absolutely crucial. That is what we are starting with. This is the mass spring model. Why does this not go? This is a mass spring model. The electrons are attached to the atoms by springs, and when I provide an electric field, the force due to the field has to be at equilibrium. It has to be balanced by the electric. I mean, sorry, by the restoring force that is generated due to the electrons being bound to the nucleus. Okay, so that is important. So that is what I'm going to write now. So basically, if my Ex, Ey, and Ez are the field components, then this Ej Ex has to be equal to a minus Kx delta Rj uska x coordinate. Is this okay? So I'm basically saying that this is the field force that is being, actually this Ej I should just take off now. This is essentially E. We do not have any J, ions are gone. This is E. Now this is electron charge. Okay, this is just electron. So this is generating a restoring force, and this is the x component of the displacement, and this is the kx money. This is the spring constant जो है उसका x component. Okay, so that means my Ex is essentially, now I will incorporate this E into this spring constant. So I will write this as some, achha, because, okay, let me write this Ej. Then this is easier to understand. This is some Kjx delta Rj x in Kjx is essentially Kx by Ej. So this is just that one thing I've incorporated both effects. Okay. So now what is this? Is nothing but the restoring force for the jth charge that is displaced by delta Rj. Okay. So now you can, I think you can guess what I'm going to write. So it is very clear that now if I basically then this total, therefore this Rj will be nothing but this vector will be Kjxi plus Ex Ey by K Kjyj plus Ez by Kjz z, right? Sorry. This is K. Ijk. Okay, so very clearly you can see that this delta Rj will be parallel to this E, my electric field E, only and only if all these kj's are equal. Because this is like that this thing you have, no? What are those called for this? अरे स्फीयर का जो ये होता है ना, इलिप्स का, अरे कॉस उसका क्या बोलते हैं उसको, अरे दैट
Eccentricity.
नो कॉस थीटा जो बोलते हैं ना, एक जो टर्म वो जो ये होता
Direction
है,
cosines.
डायरेक्शन कोसाइंस, एग्जैक्टली डायरेक्शन कोसाइंस. So these are nothing but the direction cosines, right? So these are acting very close, very similar to the direction cosines, but very crucially, what we are seeing is that this is the response. Please remember. So this is the response, right? And this is what will essentially lead to the susceptibility, because susceptibility is यही है, right? It is this इसका जो solution वही susceptibility है. So that means that delta Rj will be in the direction of incident E, or like parallel to it, only if all kj's are equal. So by the way, this is the reason, this is why you have this anisotropy present, because these spring constants are not equal in all directions. Okay, so this is extremely important. So basically that means, and why, when will this be same? This kj's will be same. Basically that implies that all displacements in or rather not all displacements, sorry. Uh, so the displacements in along all the axes have to be equal, and that essentially will happen only if there is cubic symmetry. So this is like one, or like, one depends on the other. So if the displacements are all equal, that essentially means that your k's are all equal, and that only occurs when you have like cubic symmetry of the ions in the crystal lattice.
Sir,
Okay.
I have a question.
Yeah.
Yeah. So, like, what even if this ion
Hmm.
could move finitely, even in
Mhm.
that case,
Iron nahi. Hey, Hitesh, iron is not, ions we are not taking. I'm saying that these are,
no,
the
sir.
response comes only from electrons. Huh.
That is fine. Like, listen, my argument is something else. So
Hmm,
even
hmm,
if the ions could move, the
hmm,
only that would have like that contributes to the polarization is delta Rj, right?
hmm, hmm, hmm,
That is
hmm,
the
hmm.
distance displacement of the electron from the ion.
Yes, yes.
So, like, I didn't get like, is there any need for this assumption that the ions does not move finitely or stays at the same place?
I mean, in the sense that that just complicates the problem, right? I mean, we are looking at, because see, then you need to define. I mean, okay, I mean these kJs can be ions as well. I mean, but then the whole domains are, see, typically. I mean, if you look at it in terms of physics, when you go to optical frequencies, the ions just do not respond. It is only the electrons.
No,
If
sir.
you go
I'm
to
saying in
lower
optical
frequencies,
field.
then they will respond. In that case, this kj, they will, this whole thing becomes, there is going to be one more term, because when this kj becomes like a combination of both of them actually. Okay, so
Like,
there is a
how the
restoring force for
difference would
both, but
be
what is
here, like, where exactly the difference would be, because
the
here
difference? Yeah, so difference will be this one, na? So this ej at the moment is only the charge j, which is the electron. So if this is actually the ion also, then you have a jth, and you have to basically have another running index or something. When a j is, this is for electrons, and then you have another ion contribution also coming in. So they are, in the sense that that for example, the, if you consider an electron ion pair, okay, so the electron का एक restoring force है, ion का different restoring force है, and the displacements are also all different, right? So this whole thing will basically have a kx of this electron, I mean kjx, and some kjy, okay, kjx dashed, kjx dashed, and that will probably again be some kind of a resultant, right? So you, these are not yeah, these are independent, so actually it will just be a resultant probably of that. But again, as we say that, when we typically look at this contribution of ions only come in when you look at very low frequencies, and that is actually a reason, very important, this is a reason why making polarizing optics at very low frequencies is very problematic, because the response becomes, it is, the theory becomes much more complicated. Okay, so polarizing, I mean, these half wave plates, quarter wave plates at low frequencies is extremely non-trivial. Whereas for high frequencies, this is typically works well, because essentially the response we can map very simply. It is electron response, and if you have electrons responding different way in three different axes, you have much more complicated scenario. There's no symmetry in the problem. If there is symmetry in the highest symmetry is cubic symmetry, in which case all the responses are the same. So you just, it is the same, and there's no directional dependence at all. Okay, if you have, so that is actually a practical problem. If you want to go build polarization optics for low, for very low frequency optics, it is not simple, because you cannot predict that. I don't even know whether those exist. I mean, I mean, you can have polarized light, of course, electromagnetic waves at low frequencies, but to change that polarizer, I think it is complicated, because the ions also will start responding, and then probably, I don't know. When you can look at it, I'm not sure how it will work. When you're making half wave plates, quarter wave plates at like radio waves and all that, may be problematic, very problematic. Okay. So
I think my
let
main
us go
point
to
was
the
that even if you go to the frame of reference of the ion, like the
वो
energy
ठीक रहेगा, but that
will
equation
remain
gets more
same.
complicated ना, much more complicated. वो
And
kj रहेगा, kx रहेगा,
is
सब
there any
problematic है. We
way for
typically
me to
neglect ions. So one very important thing that we are going to now look at is sort of a continuation of what we did last time. That is the stored energy of the electromagnetic field. That is very crucial because you remember last time, yesterday, when what we did was we just showed that the energy is very, that it obeys the continuity equation and all. It's pretty fine, all that. Okay. Now, of course, acha, here again we are going to look at this stored. Oh yeah, sorry. The stored energy of EM field in anisotropic media, right? So we can. So here, okay. So there is a bit of a, if okay, let us just do it. Let's see if you have issues. So I will, okay, so this is basically what you have as the, this is fine, right? This is valid for everything. And in this case, we will define this as epsilon O, epsilon this one, E dot E plus, acha, we are assuming this to be a non-magnetic media. Okay, that is very crucial. Okay, we are assuming that this is a non-magnetic media. Okay, now I am also saying, I mean, that is something which I am actually, okay, so what do you think? Can we assume that the continuity equation will be valid here? I mean, there is no reason for the continuity equation not to be valid here, right? I mean, the continuity equation is a very, very fundamental sort of a, a relationship or uh, I mean, any phenomena not obeying the continuity equation is, I mean, there is, I mean, you can have dissipation, but something like a continuity equation has to be there. Okay, this is very important to note. I mean, you can always have dissipation, but some formulation in terms of the continuity equation has to be there. Do you agree with that? Guys, do you agree with that?
Yes, sir. The continuity equation is, we didn't assume any isotropy or anisotropy.
We did
Only
not assume, right? So that's, so here, guys, there is a little bit of a thing I am playing. So see, we kind of wrote down a simple assumption for the continuity equation, right? We that was that E dot dt equal to that thing, right? I mean, E dot del d del t equal to that other thing, right? We epsilon was a constant, so we took it out. So continuity equation, there is no doubt that that is to be valid, and the continuity equation also tells us that this is going to be equal to minus del dot Poynting vector in the absence of any dissipation. In the absence of any conductive media, right, of J. Okay, if there's no J, then this is probably fine. Okay, and now there is a crucial thing that I am saying. So yesterday, we said that that epsilon naught is trivial. We are going to just take it out and all that. Now remember, what we said was, if we, for the case of isotropic media, we insisted that your this del W del T has to be equal to this E dot del D del T plus H dot del B del T, right? This is what we are. So I am actually going to come to what it will take for this to be satisfied in anisotropic media. What needs to be there? What is the crucial requirement that we have in order to say that this is equal to this. Okay, so now just think of this. So now if I just so basically this term I can write as what? I can essentially write this as epsilon E dot this. I cannot just interchange that out, right? I can only write this. Fine, this is okay. Huh? Okay, now you think that I can also, I know that this is valid. From here I can know this is this is fine, right? So from here, if I just now take, if I take this and I do this del W del T, from that I get some half of yeah, epsilon 0 epsilon R. Yeah, so this is, yeah, I'm just writing it down. Let's, you can write directly the answer, right? You can just write directly the answer. So, acha, no, yeah. So basically, just this whole thing. Let me write it down anyway. It's easier for you to note. E dot E plus B dot H. Right. Anyway, acha. Now for non-magnetic media. So basically, if if for now for
Uh, shouldn't the epsilon r be between E dot E?
So did you write the other way around? Like for the isotropic media, your epsilon r will be a simple number, so you can take it out. But in
no, no,
case
no,
of
no,
you won't
no.
be able to.
I am saying that if see, basically, wait. What I'm trying to show is, if I have this to be valid, what are the require? What is the suppose? So there is going to be some kind of a condition. Okay, there's going to be a condition that is going to come. Okay, so that is what we are trying to derive. I'm saying this is for isotropic media. That is fine, right? But in case this is right, then there are some conditions. Okay, acha. So we, okay. So what? Okay, what Anish is saying is that
So D is epsilon r. I mean epsilon naught into epsilon r E, right? So and that epsilon r is a tensor. You can't.
Wait. So
Epsilon r E.
yeah. So D is epsilon R. D is yeah. Wait. So yeah, if we can write
Or
this
you
as,
can put
okay. So
brackets around. You can put brackets around epsilon r and E. So like epsilon r E dot E. Like
yeah.
like it doesn't or at the
So you're saying that yeah, this goes there, huh? Okay.
I'm just
So
saying these are
epsilon
brackets.
R dot E.
Epsilon r. Put
Yeah,
bracket around
this
that.
one, right. Yes. So you're saying here, okay, I need to put a something like this.
Yeah, that.
Yes, that is correct actually. That is probably correct. Okay, that is probably correct. I think there is. Anyway, so for non-magnetic media, we know that. I think they will. Let me see. I think I am not very. Anyway, so you know that for this one, mu r is 1, and B is your mu 0 H, and so clearly your basically this B dot del H del T is the same as H dot del B del T. That is very clear, right? Which means that you know that right. So I can write this half of del T B dot H. I can write as H dot del B del T. This is fine. This is absolutely fine. So now, so basically, if I now take this, actually it doesn't matter. Okay, it doesn't matter. So now if I just think of this, if I take this half of, now if I take this epsilon naught epsilon r E dot E, that is basically, okay, now this one, you just check out if this we can write. del E del T dot E plus E dot del E del T. Is this okay?
No, sir, I don't think so. Like again, when you take the dot product, you'll already get a scalar. Like epsilon r
In
has
the
to.
sense that no, so what we are doing is that I'm saying that this epsilon r, this thing, I'm just saying that this is del E dot this thing. And next time I'm saying that I'm keeping this constant and taking this one. It's okay, no? Because I'm taking this as one whole thing, no? So I'm first doing iska derivation, and there is no this has no time dependence. This is fine. Okay, so I'm just from here. I'm
Fine.
saying that once I'm del E del T dot E, then E dot del. So epsilon r is multiplied on this side, on only on this one, only on this one. Is this not okay? I think this is okay, no? I'm keeping the
So the
metric on the
brackets
same
on the
side.
left hand side seem wrong.
The
If
here.
it should be epsilon r del E del T brackets dot E.
Acha, so you're saying this one and no, but here, but it's same. No, I'm saying that this is at this tensor is on operating on this one, only on this side and on this one, right? So basically, what I'm saying is, okay. So you are saying for strictness, I put something here and then I put this one, but it's the same, Anjut. Come on, I think it's same.
I don't no, I don't think it's same. Like epsilon r, like
So
when you
I'm
del
okay.
E
You're
del
saying that it
dot.
can multiply to any one of them.
No, so I'm not. I'm saying it's not associative.
It is not associative.
The
Okay,
brackets are
so
important in
R
this
is
case,
a
according to me.
tensor, that is, it's a matrix,
uh,
and your
what?
electric field is a
Uh,
vector. So
uh.
here your this matrix algebra is wrong. I think that's what he is trying to say.
No, so what
Because
he's
this
saying,
is
I
not
understand. So he's
coming from
basically
the
saying that this one, this thing should go, and I should put this. Uh, this and this, right? Something like this.
Yes, sir. I think now just
Yeah, this is what you're saying. Okay, okay, TK boss. Okay, so that is the same thing that we have here, no? So that you will agree that this term and this term are same. That you will agree.
yes, sir.
Rather, this that is fine, right? Okay, okay. Then you are correct. Then I must say that this is so basically what I should do is I should just write this, and this. Okay. So now we know. So now if so basically then so this as you see here. So this is E dot del T and this is also E dot del T. So basically this whole thing, this part has to be same as this part, right? If this is valid, if I say that del W del T is equal to this, here also del W del T is equal to this, right? So both cases del W del T is equal to this. So this and this are same, right? So this term and this term are same. So then this term and these terms also have to be same if I claim that this relation is valid. This, remember, I had got from the that pointing vector thing that we had done before. Okay, so that basically means that I can write this as equal to epsilon naught epsilon r e dot del e del t, which basically again implies that I have to have this is very crucial. Is this acceptable? This is the condition. This is the crucial condition that we need to impose in order to have Both this is of course true. This is absolutely true. This part is there is no doubt. This has to be true. From there I get this. But this one I too wrote, this term I wrote, assuming the continuity equation. Right? This is the electric field for this is absolutely standard definition. And if I just take the del W del T, I will get something like this. But if I assume the continuity equation and the thing for isotropic media that I wrote that time to hold in the previous class to hold, I have to have this valid. This has to be valid. And this is what I want you to prove. This is very crucial. I want you to prove this for the next class. Very crucial. So prove this. Right? So basically what prove what? That epsilon r del E del T dot E equal to epsilon r E dot del E del T. So essentially what you will get is this xx xy what sorry yx zx this ex dot ex y dot z dot this is equal to the same thing that there. So can we just sort of yeah, so we will define the index ellipsoid then in the next class. This is where it comes from. So please prove this. Show that this is your one. That one is valid. Okay, so you will find that in order to have this two, this is this part okay? Huh, guys?
Which part?
I mean, this relation you agree with, right?
Yeah, yeah.
So this, please show this. It's very simple to show, but there will be some very interesting properties that we shall derive from here.
Sir,
Sir,
Okay, so basically, huh?
sir, am I audible?
Yeah. Hello. Hitesh, bolo.
Sir, like this is just like saying the transpose of left hand side is equals to uh, the number which you are taking the transpose of. So left hand side is a
Correct.
scalar and right hand side is also a scalar. So taking a transpose
Right.
of a
But
scalar
what is
means
the condition that it imposes on epsilon? Can you say that?
on epsilon.
Yes,
It
that it will impose a condition on epsilon.
Sir, the thing is actually you have to like it like you have to properly write it down in the matrix language.
हाँ
It's
वही
like
तो मैं बोल रहा हूँ करो वो
expect is
करो
this epsilon r has to be symmetric.
exact हाँ
Epsilon r
very
has to
good yes correct but prove that okay
okay.
just prove that can we if you can do it in one line that's also great then just whatever you show that I mean I want you to prove that epsilon what you said basically
Okay.
okay just prove that if it's a well you can do the hard way that is by multiplying all these three that I showed but if there is a simpler way I will be very happy to know I will incorporate that in my notes so please if you guys can show this of course you can multiply these out and do but if you guys can actually show that in a simpler way that obviously what Hitesh said that is correct it is going to be symmetric epsilon xy is going to be it's a symmetric tensor basically so if you can show that in a simpler way I will be very happy I will put that in the notes but that is something after that we'll define this crucial I could have finished it today but forget it it's okay it's late very late in the day okay
sir,
so
sir, can you go back to previous board?
previous one huh
In
bolo
the in the last step where we
Hmm.
take do the product rule of the time derivative, how
So
did you
product what?
this now
This
half
one,
of
this step. Ah,
yeah
So this
yes.
also is half. Bolo.
So my point is you took the time derivative for the first
Hmm.
component and then multiplied in second. Why did you assume that the epsilon is time independent?
The property of a crystal cannot change with time. Right?
Like,
That is
are
the
we?
property of a
Yes,
crystal, right? That cannot
we
change with
can
time.
always have systems where we can change properties with using like.
That no, that I okay, no. That is
I'm
something.
just
See, the
asking you to
response
assume.
is always no, no, no. That we are absolutely not assuming. No, this is absolutely not going to change. See, because then that is it's quite crazy, right? If you actually have the same thing and then you're shining light and it becomes different, then it's going to be you cannot do anything on it, right? Then your quarter wave plate will change at different instances. See, Rohan, there is a difference between my response being different for different fields. That is okay. But the properties for the same field cannot change with time. So if
Like,
I'm not changing
they
E,
generally do
I
not and
cannot
they cannot. There is a difference in that, right?
cannot. Yes, yes, yes. That is crucial.
Okay. And then
Okay, that is
I
very
couldn't
crucial.
understand the last step how you wrote that
No,
those
so
two.
this is basically this one. No, so this is what we had last yesterday. Right? I mean, the yesterday we wrote this. Rather, yesterday we wrote this. Right. So this means this.
And after that,
This means
what
this.
happened to
And
the
no, then what we did was this one. We are considering this one. This is correct definition of field, right? Of field energy density, right? Stored energy density is always this. Then I do the time derivative, and we very carefully write down all these matrices. These things have to be very correctly written down, right? And then I know that this part is the same, exactly same as this part. So then what I get for this part, this part, that has to be same as this part, right? Now if you see, I have a half this one and this one. So this is also there. So that means this and this are same, right? Which means then if I now equate this whole thing with this one, that is this, right? So this one that you have is this, right? So let me put a red dot. So this is this, right? So then if I equate these two, then this half gets cancelled. So you have this impose, the condition you impose is this has to be equal to this. So this I
why
am asking you to verify.
why are we equating the part from isotropic media to the anisotropic part?
No, I am saying that is what I'm saying. If I assume, see, yesterday I told you that we are doing that, we took that epsilon not out and just said whatever. So in the sense that, no, but remember again that this was something that came from, so again, if the continuity equation is valid, Hitesh, then sorry, Rohan, then this has to also work, right? Because I can always write the del dot E in those vector addition form, right? So if I
Oh,
assume this to, if the continuity equation is valid, then
hmm,
this forms, right? So this has to come from there. And I can write this to be that E dot del cross H plus all that stuff, right? So
okay.
that means this has to be valid, right? So if this is valid, that sort of imposes some condition on epsilon. Yes, on the conditions on epsilon, which Hitesh has already given the answer, but I'm asking you to derive that. What condition it imposes on epsilon?
Okay, sir.
Okay,
Uh,
this is what I'm saying.
can you like give me some reference where to read this from?
I'm going to upload both the references. Okay, I have two references. I'm going to upload
Okay.
both of them.
Okay, sir.
Okay. Thing is that some one there. I mean, yeah, there are some. I mean, they are not complete. Okay. I mean, I have taken from both, so you have to study both very carefully. I will upload today's notes. With today's notes, I'm going to upload both the sources that I'm using.
Okay.
Okay. Okay. So please do this proof, and we shall meet on Thursday. And let me see how much I can cover on Friday, on Thursday. If I can cover something, I mean, where we can see some end in sight, then I'm going to take the Friday class and finish this. isotropic this thing. No, I don't think I can cover actually. There's a lot of things left. No, I don't think I can cover in two classes. Yeah, it is. Let me see. So depending on, I don't think I can cover. Yeah, okay. That is, if we have to reach some kind of closure on Thursday. Okay, some kind of closure we need to reach. Otherwise, it is difficult to continue. I mean, otherwise it's completely zero से start करेंगे तो problematic. Okay, ठीक है. Okay. Bye for today.
Sir, I had a doubt in the
Okay, so
portion.
today, just 1 second here, Anubhav. So this is going to be at Pratik